This presentation is on the characterization and establishing the dissolution kinetics for the rare earth element ore at the Nechalacho deposit in the Northwest Territories. The global climate crisis has created a need to shift to green technologies in order to lower the carbon outputted to the atmosphere. These new technologies require resources that are not commonly mined, such as rare earth elements. Rare earth elements are used in rechargeable batteries, windmills, and many other technologies. The mining of these elements is uncommon, and thus their supply chain is poorly structured. They are considered critical minerals because of this. A critical mineral can be defined as minerals that are resources needed for the economy but whose supply may be disrupted. Among many other elements, rare earths have been added to Canada's critical mineral list this year. Other countries have also deemed rare earths as critical minerals, which is easily understood by looking at the distribution of production of rare earth elements by each country. Easily dominating mine production in 2021 is China, producing 140,000 tons of rare earth ore. This creates a large dependency on a few producers with a very unstable supply chain. That, combined with complex geopolitical issues, Canada will greatly benefit from a domestic source of rare earths. Canada has over 15 million tons in rare earth ore reserves, and there has been no production until this year. The Nechalacho deposit in the Northwest Territories is currently the only producer of rare earth elements in the country. It is located about 100 kilometers southeast of Yellowknife on the Hearn Channel and is a part of the Thor Lake deposit, which is endowed in many rare earth element resources. This deposit is split into many mineralized zones, the T-zone being the focus of this study. This Paleoproterozoic deposit is host to many rare metals such as yttrium, cerium, lanthanum, niobium, tantalum, zircon, and beryllium, which are hosted in an assemblage of alkaline, syenite, and granite. The T-zone of the deposit is the northernmost part of the deposit, and it consists of heavily hydrothermal pegmatite. The alteration of the T-zone is characterized by replacement of primary mineralogy and abundant pseudomorphs. The main ore mineral that is being mined at the T-zone is bastnaesite, a rare earth element bearing fluorocarbonate mineral, which is seen here on the right. This small open pit operation began in June 2021 by Vital Metals with crushing and sorting of the ore done on site. The ore is then stockpiled and sent to Vital Metals processing facility in Saskatoon. Since this is a first of its kind mine for Canada, there is a lack of environmental policies for rare earth elements both here and globally. There is no drinking water regulations as rare earth elements are not included in the metal and diamond mining effluent regulations, as the behavior of these minerals is not well documented. The most knowledge of fluorocarbonate minerals comes from metallurgical practices aiming for the optimal leaching of rare earths from the ore. There is little knowledge as to how these minerals react at Earth's surface conditions, and there are no established solubility or dissolution rates for bastnaesite. The objectives of this research project are to characterize the main ore mineral at the T-zone of the Nechalacho deposit, and this will then aid in determining the dissolution kinetics of bastnaesite and finally predict the rare earth element release rate at Earth's near-surface conditions. The samples for this research were obtained by the Northwest Territories Geologic Survey and sent to Queen's University. They are collected from a decline at the T-zone consisting of the ore mineral. These samples' bulk mineralogy can be seen in hand samples as quartz, fluorite, carbonate mineral, and bastnaesite. These samples were used to make thin sections of, and seen to the right here is the representative texture of the samples containing mostly bastnaesite under cross polars of a petrographic microscope. Intergrown with the bastnaesite is another rare earth element bearing fluorocarbonate mineral, parasite. This mineral is greatly similar to bastnaesite, with the only difference being the existence of calcium. The most common texture of the bastnaesite-parasite mix is a blocky to platy texture, as seen here with the SEM-BSC images. The grains of bastnaesite and parasite are both elongated with distinct grain boundaries, and the texture here suggests the replacement of one mineral by the other, commonly seen with a quartz matrix. On a larger scale, the extreme complexity of the intergrowth of the two rare earth element minerals can be seen. Near carbonate phases, such as the image to the right, the texture of the parasite changes. It takes on a more rounded grain boundary. The texture of the bastnaesite and parasite is also affected around inclusions of quartz grains, becoming heavily fractured near contacts with it. This creates a greater surface area for reaction to occur, which could then affect the dissolution and solubility kinetics of these minerals. Electron microprobe analysis was utilized on 5 thin sections for a total of 132 analysis points. This was used to get relative weight % oxide of the rare earths in the bastnaesite-parasite mixture. The presence of monazite among the bastnaesite-parasite is observed as seen here. However, a majority of the analysis was focused on the ore minerals rather than the monazite. As seen here, the average rare earth element oxide weight % indicate that the bastnaesite is enriched compared to the parasite, particularly with lanthanum, cerium, and neodymium. With the smaller oxide weight %, the bastnaesite points in the parasite are quite similar, so there are blue bastnaesite points behind the red parasite here. The small error bars for the values close to detection indicate that there are no outliers in the bastnaesite or the parasite analysis points. The enrichment in calcium is also indicated here as their only elemental difference in the two formulas. The low concentrations of thorium from this analysis is something to note, especially in concerns to the environment and drinking water regulations. It came up near close to detection in this analysis. When normalized to a chondrite, the bastnaesite, parasite, and monazite display almost identical trends in light rare earth enrichment. The monazite preferentially has erbium compared to the others. Normalizing to a chondrite relatively compares the concentrations to the most primitive rock of the solar system, thus emphasizing the rare earth element enrichment. This indicates further that none of the rare earth elements prefer either bastnaesite or parasite, and the difference in the averages of weight % oxide seen before must have been attributed to paragenetic processes. The bulk mineralogy of these samples was determined using X-ray diffraction analysis, which indicated that the bastnaesite, parasite, fluorite, quartz, and albite are the bulk phases present. As monazite was not detected using X-ray diffraction analysis, it is not considered to be a major phase in the samples. In order to establish the dissolution rates of the bastnaesite, it must first be separated from all of these other minerals. This will be done in 2 steps, the first being the use of a self-rig, which utilizes ionized water to separate minerals in a rock along their grain boundaries. The result of this process can be seen here to the left as a mixture of the bulk mineralogy separated from each other. Next, a Jasper table is used to isolate the bastnaesite. A Jasper table operates the same way as a Wilfy table does, just on a smaller scale. The sample flows down the table from the left to the right in a solution of tap water while the table shakes, separating the grains based on their relative densities. Once completed, the samples are decanted and dried in an oven at 75 degrees Celsius for approximately 24 hours. The product of this can be seen with the naked eye to still have impurities in the bastnaesite collected, so only the most pure sections collected from the table will be used in the experiments, starting with the batch experiments. Post-mineral separation, the samples were analyzed again using X-ray diffraction. These results indicate that the mineral separation process successfully removed the albite from the samples. However, the removal of the parasite, quartz, and fluorite will require more techniques. For the purpose of this research, this is the extent of the mineral separation that will be done. Using more complex separation methods with solutions other than water will likely alter the natural state of the bastnaesite and parasite, making the results of the dissolution kinetics not applicable to near-Earth surface conditions. The samples run in the future experiments will contain quartz and fluorite as well as the rare earth element ore, bastnaesite, and parasite. The preliminary experiment performed on the bastnaesite-parasite mix was a batch experiment to determine the release of rare earth elements over time at different pH levels. Half a gram of the bastnaesite-parasite mixture was added to approximately 950 milliliters of a solution at 20 degrees Celsius. The reactors were monitored over a 14-day period and sampled for 10. The pH was measured every day as well to track its change over time as the mineral dissolved. The chosen 3 pHs for these reactors was 2, 4, and 9. These were chosen to give a wide range of conditions to better understand the mechanism of dissolution. pH 9 is the most similar to the lake water conditions in the Thor Lake region. which is why it was chosen. A common weathering agent is rain, which often has an average pH of 5.5, which is the closest to our pH 4 condition. Conditions of pH 2 are an unlikely near-surface condition in the natural environment, but it is the most likely to see any mobilization of the rare earth elements, which is why it was chosen. The results for this experiment are still under investigation with results from an ICP-MS and the ICP-OES. The results from the batch experiment at pH 2 conditions exhibit rare earth released over time, starting from the very initial date when the mineral was added to the solution. The 4 rare earth elements with the highest concentrations in these samples are further proved by these results and are praseodymium, neodymium, cerium, and lanthanum, which show the greatest release over time in the reactors. Please note the log scale of these charts of the sample day over the concentrations in ppb. At pH 4 conditions, the same trend is not seen as in the pH 2 conditions over time. The quantity of the rare earth element dissolved in these reactors is on a magnitude of a difference as seen here. Conditions of pH 9 show negligible dissolution of the rare earth elements and no common trend between the elements. However, it still does have the highest concentrations of those 4 rare earths as before. To conclude, bastnaesite and parasite are the main ore minerals in the North T-zone of the Nechalacho deposit. These 2 minerals are intimately intergrown and for the purpose of this research will not be mechanically separated. The bastnaesite is enriched in rare earth elements compared to the parasite. The dissolution of these mineral mixtures is strongly pH dependent, with more acidic pHs, such as pH 2, showing more dissolution than the higher pH at pH 9. Future work for this project includes continuous characterization of the bastnaesite and parasite to establish the relative amounts of distribution of rare earths in each phase. The batch experiment results will then be utilized to structure the dissolution flow-through experiments used to establish the solubility and dissolution kinetics of these minerals. These results will be used in the future to predict the environmental impacts of rare earth elements at near-surface conditions. Thank you very much for listening.